6.7, sinusoidal functions as mathematical models. Your essential question is, how can sinusoidal functions be used to model, make predictions, and interpret real-world situations? So I don't know how often you're going to be using water wheels in the future, but just in case you are, here is an example that involves water wheels. But as you've seen from the explorations that we've done, we did an exploration involving chemotherapy or radiation treatments, and we've also done one with oil wells underground. So those are both also applications, and you'll get to see a bunch more problems. All right, we are not going to, you don't need graph paper. I'm going to use graph paper, but I basically wanted to give you this handout so that way you had the problem in front of you. It's also in your book, and they also work it out in the book as well. All right, so the water wheel problem. Suppose that the water wheel in this figure over here rotates at 6 revolutions per minute. That's important. So I'm going to write that down over here. I'm going to call it 6 revs per minute, which means it goes around 6 full times in 1 minute. Okay, 2 seconds after you start a stopwatch, point P on the rim of the wheel is at its greatest height, which is D equals 13. Okay, so I know that, let's see if I wanted to think about a table. When time is 2 seconds, my height is 13 feet, or my distance above the surface of the water. The center of the water wheel is at 6 feet above the surface. So the center here is 6 feet above the surface. But notice your radius here is 7. So at some point when this water wheel comes around, it is underwater, hopefully you're recognizing, by 1 foot, right? Because your radius here is 7 feet. All right. Sketch the graph of D as a function of time t in seconds since you started the stopwatch. So I'm going to use graph paper. You don't have to. You can do it right on here too. But just to be more exact. Oops. Oh, let's see here. Okay, cool. I did a good job. So this is going to be a height of 13, which is my max height. This is the D axis. Let's see. And then this is my T axis, which is in seconds. And this is in feet. All right, so the center of my wheel is at 6 feet, right? Let's see, from the ground. Okay, so that tells me that my midline is going to be at 6 feet. And then I know that at time 2 seconds, I'm at my highest point, which is 13 feet. So what's my lowest point? Well, from 6 up to 13 is 7. Right? And that radius of that wheel was 7 feet. So if it's only 6 feet off the ground, then as I come around, I'm down below 1 foot. So I know that my lowest point is going to be at 1 feet, or 1 foot. Okay, the question is, what's my period? So I get 6 revolutions per minute. Okay, or in other words, I can rewrite that as 6 revolutions per 60 seconds. Since my units for time are in seconds, it's probably a little bit better for me to go with 60 seconds. Now, can I reduce this so that I get, how long does it take for me to do 1 revolution? So I can divide, and I know that in 10 seconds, I can do 1 revolution. So basically here my period is 10 seconds. So that helps me figure out where my next highest point is going to be. My next highest point, the next time I'm at 13 feet, is going to be 10 seconds later. Which is at 12 seconds. putting my lowest point halfway between those. And remember, my midline, or my sinusoidal axis, was at 6. Now my lowest point's at -1, and it's going to be halfway between 2 and 12. Well, to find the midpoint between 2 and 12, we add them and divide by 2, and we get 7. Right? That would be 14 divided by 2 would be 7. So 3, 4, 5, 6, 7. Now, when am I on my sinusoidal axis? Well, that's going to be halfway between 3 and 7. Right? That's going to be the halfway mark. So that gives me 10. So it's at 5 that I'm going to be on my sinusoidal axis. I lied. It's not between 3 and 7. It's between 2 and 7. Right? Because my highest point is at 2, not at 3. My bad, sorry. So it's halfway between 2 and 7. Again, averaging those, or finding the midpoint, is 2 plus 7, which is 9. And half of that would be 4.5. So I was close, but not exact. And then doing the same thing between 7 and 12 to figure out where I'll be on the sinusoidal axis there. That'll give me 19. Divide that by 2, that's 9.5. So I have a pretty good idea that this is going to look something like that. And that'll keep going on. Okay, so that was A. Let's see. All right, and then we're going to assume that D is a sinusoidal function of t. Write a particular equation confirming by grapher that your equation gives the graph. All right, so we've already figured out what our period was. We know, let's see, so our sinusoidal function, I'll use cosine, and we're going to use t. Oh, and actually, we're using distance instead of y. Otherwise, I just went ahead and plugged in everything that I usually use. So our midline was at 6. Our amplitude, well, that went up 7, right? Because my radius was 7. So from 6 feet, I went up 7 to get to my highest point, which was 13, or to my lowest point, which was -1. To find B, that's going to basically be 2 pi over my period, or pi over 5. And then my horizontal translation was 2 seconds. Right? So my highest point, if I'm using cosine, that's what I care about. Otherwise, you'd be using this point here for sine, which would be 9.5. Okay, so B, I'll go ahead and write on here on my graph paper, just so I have nice and clean. So now I'm going to confirm by grapher that this equation, in fact, does look like this graph. So I'm going to have 6 plus 7 cosine of pi over 5. So I'm going to put that in its own set of parentheses, times the quantity, which I'm going to put in its other parentheses, x minus 2. I'm going to close both sets. Let's see here. Oh, and I should probably think about my window. So my y-axis needs to go up to at least 13. So I'm going to say, how about 15? And down to at least -1. So I'm going to say -5. That's fine. Now, let's see. Let's put a couple periods on here. So another period would take it to 22. So why don't I do x max of 25? And x min will be -5. All right, that looks pretty close to what I've got. All right, so that checks out. So now, part C is how high above or below the water surface will point P be at time t equals 17.5 seconds. And at that time, will P be going up or down? So I can do this a couple ways. I can just use my grapher. So if this was 7, let's see. Oh, actually, I could do 17.5. Why don't I just trace it? So right now I'm at like 15. So 17.5 is somewhere right around here. And it looks to me like it's going to be increasing. I could always zoom in right there. So there's 17.3, 17.4. Oh, perfect, 17.5, because I zoomed in, I was able to get there. Otherwise, I could use my table feature, which I'll do that next, just to make sure. So I get at x equals 17.5, or I should say at time equals, then d equals negative 0.806 feet. However, the graph I can see is increasing. So it's going up. Now I'm going to double check that. That is not the answer that I originally got, and that is not the answer that my other calculator is giving me. So let's just go ahead and let's do a table set. We care about where it is 17.5, where x is, right? And I can just increase, oh, it doesn't even matter. And then I'll go to my table. Yeah, so the trace feature doesn't always give you the most accurate values. So it's probably a good idea to double check on your table. And I cannot explain why there is a difference there or a discrepancy. It's not much, but it's enough. Okay, and if we were dealing like with millions of dollars, that could make a huge error, right? So it's actually negative 0.6574. But we're still in that same part of the graph, and we can even see from here that as we increase, it's going up, right? And if you wanted to be a little bit more precise about that, maybe the way that I was originally doing it, I could have done 0.1. And then you can even see from the table, oops, I didn't hit. Let me get the table going one more time here. You can even see from the table that it's increasing, right? So your distance is getting less negative, which means that the wheel is going up. Okay? All right, and then we're going to do D. At what positive time t does point P first emerge from the water? Okay, so at what positive time t does point P first emerge from the water? So I'm imagining that they're talking about in this area, right? Okay, so sometime after 7 seconds. So that's what we want to look at. And it's at -1 feet, or it's below water a foot at 7 seconds. And really what we care about is after, and it's emerging. So right after it comes from something, basically it's got to be a height greater than 0. So we could do this a couple of different ways, but maybe what we want to do is work with our x-intercept. Let's go ahead and find our x-intercept here. So I'm going to go back to my graph. Oh, I better go back to a standard window. Let's see, zoom. Oh, I have to change my entire window actually. So back to my maximum. My minimum was like -5. I did 2, so how about 20, 25? I'll start at 0. Okay, I'm going to calculate my x-intercept right here. Oops, what have I done? Second calc is what I wanted. I want my 0. I'm going to go left bound of it. And I'm going to go to the right of it. .86. So right here, this value is approximately 7.861. And again, I guarantee if I was tracing, I would not get that exact number. I'd get something close, but not exact. Okay, so at D, at what positive time t does point P first emerge? So at t equals 7.861 seconds. Okay, we're done.